Anyway, without any further ado, one thing I just want to make clear is that this is mostly not going to be an engineering talk. So there are a lot of really interesting engineering problems that we've discovered along the way of doing all this genomic work and trying to translate that into the clinic. But I'm mostly not going to be talking about those. The point of this talk is to try to discuss some of the interesting research problems that I think are posed for computer science by the advance in genomics. However, if you are interested in engineering problems, I'm also going to be speaking at our Counsyl info session in a couple of days, and the info for that is right there. So if you'd like to find out more about what we're doing in the engineering area, if you're looking for a job, I'll be speaking at 7:30 on Thursday in the Horizon room in the Career Services Center. So to get along with the talk, I was trying to figure out what I wanted to use as a theme, and I decided to put up music that I like. Have any of you heard this album? All right, great. So this is Stillmatic, a rap album from Nas, and one of my favorite songs on it is titled Rewind, and it's a rap song that goes in reverse. So if you've seen the movie Memento, you sort of know the principle. You're starting at the end, trying to reconstruct what happened at the beginning. Similarly, Nas is telling the story from the end. And I'm going to do the same thing. I'm going to spit the story backwards and start at the ending. So what's the end game for genomics and computer science? The genome will be pervasive in medicine. So if we assume that is our conclusion, what are the implications? First of all, let's just try to bound this by getting an order of magnitude estimate on how much data we're going to need. The UN predicts that in 30 years, there are going to be about 117 million births per year across the entire world. That's basically the product of the total population at the time times the birth rate. Each person's genome is bounded below at 750 megs of data. That's just if you take 3 billion base pairs at 2 bits per base, that's the amount of data that you get. As I'll point out later in the talk, really you're going to need more than this in order to get any reasonable amount of information out of a person. You might object, certainly even by 2045, not everybody is going to have their genome sequenced, but I think the two can roughly cancel out. We'll say there's at most a small constant factor. Let's say it's about 750 megs. What that means is that in 30 years, we're going to have roughly 3 gigabytes per second continuous of new genomic data coming in. That's 4 genomes per second of every day. Now, this is only looking at the new population, so just kids who are being born all the time in 2045. You might also ask, well, what about the current population? That's 9 billion people in 2045, 6 to 7 billion now, but in computer science, that's order of 1, so we don't worry about that one. So what's the point of this talk? I'm going to start out telling you my reasons why I think genomics is going to take over medicine, both in what we sort of traditionally think of genomics as well as other applications that are really going to revolutionize what we do. Next, I'm going to talk about what we, and when I say we, I mean computer scientists, need to do in order to get us up to this 4 genome per second rate and actually be able not only to acquire the data, interpret it, but also translate it into the clinic and make it usable. And so I'll structure that around 3 points. How we acquire the data, how we analyze it, and how we get it out there. But before we get to all that, maybe I should explain a little bit about who I am, where I'm coming from, and why I'm even talking about all this. So who is Counsyl? What do we do? What we've done is we've developed a single genomic test that replaces 100 different expensive assays. So genetic testing is already recommended by the medical community for a number of conditions that are extremely severe, known as severe Mendelian recessives, which are genetic conditions such that if you inherit 2 defective copies of a gene, then you will have the disease. It's not something where you're just getting a small additional risk or something like that. The key innovation that we've done is that we're able to test many different conditions all at once in a single test. As a consequence of that, we've reduced the cost of carrier testing by over 100-fold. The test has acquired quite a bit of external traction. Both the Wall Street Journal and Scientific American have honored it with a number of awards. But really, the main thing here is just the efficiency of doing this sort of multiplex testing rather than the single gene testing that's been predominant to date. So if you look at a couple of our big competitors, Quest Diagnostics and LabCorp, and you look at their price sheets for genetic testing, what you'll see is that all these diseases are listed on a per disease basis, and every one of these is over $100, most of them in the $200 to $300 range. Similarly for LabCorp, you get the same sort of amount. So you're talking about $5,500, $4,700 for panels of 15 to 30 diseases from Quest or LabCorp. The cash price for our test is $349. So really, you're talking about a huge difference. what we've been able to do is disrupt over $5,000 worth of existing testing. As a consequence of that, we're now testing over 2.5% of all the births in the United States. We have nationwide coverage, and because of this, and because of our exponential growth, we recently tested our 100,000th sample. So that's the sort of data set that we're coming from. To give you a little bit of an anecdote, it's really nice to work at a place where you have that kind of data, because when you're doing fun machine learning problems, it's like working in the mythical land of infinite data. You can set up a training set, run a test set. When the test set doesn't work, you need to tweak your model parameters. Oh, look, it turns out the lab generated more data, so it's really fun. So why is medicine going to take over genomics? Continuing the theme, a lot of you have probably heard this album, Jay-Z and Kanye's recent collaboration, Watch the Throne. I'm going to argue that what we should really be doing is watching another throne, where medicine is being challenged by the young gun of genomics. And we need to figure out why genomic tech is really going to take over. So let's consider the state of the art in genetics right now. What I've described with what we're doing at Counsyl really is pushing the frontier of what's possible right now, but even then you might object that it's fairly simple, right? We're only testing for these Mendelian conditions that have relatively simple inheritance patterns. There are other companies that are doing other sorts of genetic testing, like 23andMe looking at genome-wide association studies, but they also can't make very strong predictions. They're usually looking for small risk factors. So what can we do other than just carrier screening? Well, one big example is the burgeoning area of pharmacogenomics, or targeted medical therapies. Really, the first drug that came out of this class was Herceptin for breast cancer in 1998, which is an antibody that is effective only against cancers that express the HER2 protein. And so you actually have to have a genetic test before you can decide whether or not Herceptin is going to be effective for you. A few years later, imatinib came out, also an oncology drug. So this is a drug against chronic myelogenous leukemia that targets, again, a very specific gene mutation known as the Philadelphia chromosome, or BCR-ABL fusion. So this gene fusion is actually responsible for most of the cases of this disease, but it's not present everywhere. And so again, you have to have a genetic test to make sure that it's actually relevant. In 2005, there was a really interesting case where two existing drugs, isosorbide dinitrate and hydralazine, were under clinical testing as a combination drug against heart disease. And what the trials found was that this combination didn't have a measurable effect better than baseline drug performance in any population except in African Americans. And so this combination, known as Vital, was extremely controversial at the time, but eventually did get FDA approval to be marketed only for use in African Americans. So another example of what is essentially some genetic-based characterization of drugs. And most recently in 2012, Vertex Pharmaceuticals won approval for their drug ivacaftor, or Kalydeco, which is a cystic fibrosis drug, but which is only effective against certain versions of cystic fibrosis. So ivacaftor is only prescribed, or is only indicated in cases of CF that are caused by what's called the G551D mutation. It's not effective for other more common mutations, such as deletion of phenylalanine 508. And so really what we're looking at is a new generation of targeted drugs, but ones that are still fairly narrow. We understand what's going on, but we can really only understand them in the situation where we're looking at single gene traits and there are very simple inheritance patterns. Now, the problem is, how do we get from this sort of single gene stuff into this new interesting world of genomics, and why do people care? I'd like to show you a graph that some of the people in the field have probably seen before. They came from the National Human Genome Research Institute. What this plot shows is how much it costs in order to get a raw megabase of DNA sequence. So that's before you've done any sort of error correction, just raw data coming off the sequencer, and how that's scaled with time. You'll notice on the y-axis that we have a log scale, and the white line over here plotted is Moore's law. So it's a simple line because Moore's law is this exponential that halves every 18 months. What you'll see is that for a long time, up until about 2007, sequencing was roughly following the cost of Moore's law. But then in 2007, the floor came out from underneath. And since then, the cost of getting DNA sequence has been crashing far, far faster than you would expect from Moore's law. If we started in 2007, we're looking for that raw megabase, and sequencing scaled as fast as silicon technologies have, then today it would still cost us over $100 to get that raw megabase of data. Instead today, it actually costs us about 10 cents. That's a huge difference. There's an old saying that says that if you build a better mousetrap, somebody's going to use it, right? And it's a similar thing when it comes to sequencing. Cratering prices are going to drive technological shifts. Fundamentally, if we can do something with DNA, and it's so cheap to do so, then it makes economic sense in order to do that. So what's going to happen? One thing that's already started is work on whole genome association studies. So this is something that's very popular in academia and has been commercialized in a few places. 23andMe is doing a lot of SNP mapping in order to do whole genome association studies. Decode Genetics is a large body of data from Icelandic genetics where they're trying to find causes of disease. And fundamentally, what these studies are looking at is to try to find associations with disease and human health that can't be tied down to a single gene or a single point mutation, trying to make more sense of the entire 3 billion base pairs of DNA that we have in our genome. Another very interesting area is RNA-seq transcriptomics, and I think here you can also consider epigenetic sequencing as well. So when I mentioned 750 megabases of data for the human genome, that was a static estimate. That's sort of the DNA that you're born with that doesn't change, except for maybe occasional point mutations that cause cancers and so on. But in reality, our bodies and biology in general are highly dynamic. And the way that a lot of that dynamism is expressed is through gene expression. And so people have been doing gene expression assays for a long time using things like RNA microarrays. But RNA-seq is a much more recent development where you're actually sequencing all the populations of RNAs that might be in a cell. And in transcriptomics, you're basically measuring all the transcript levels that you can all at one time. Similarly, epigenetic sequencing is looking at the changing epigenetic markers, such as methylation or histone acetylation, that occur in DNA, which can change over time, which have dramatic effects on gene expression. So why is this interesting? Because now no longer are we talking about just 750 megs that maybe you sequence when a child is born and then never look at again. In reality, we can get a lot more data out of that when you look at genomics as time series data. Finally, we don't even have to consider just human genetics. So there's a whole host of other microorganisms out there. For example, one thing that you could consider would be changing how infectious disease diagnosis is done right now. There's been a lot of work, especially out of labs such as Joe DeRisi's lab at UCSF, trying to use genetics and microarrays to diagnose, for example, viruses, to try to find out when you have a new strain of a virus, whether that cold is a common cold, the flu, or the next SARS, and so on. Similarly, metagenomics is the ability to try to take an environmental, bacterial, or other population and just find out what's in there. This is getting a lot of attention even in the human context now, as people are probing the microbiome inside humans. So for example, the bacteria that live inside your gut, or the bacteria that live on your cells. This is an incredibly interesting area. So just a couple of weeks ago, actually, there was a paper that came out that showed that postulated that obesity might actually have an infectious cause. What they found was that there was a population of Enterobacter that lived inside an extremely obese patient. When they put that patient on a special diet, most of these bacteria died off, and then that patient lost weight. But you could say, okay, whatever, that was just a diet. The interesting thing was when they took these bacteria and transplanted them into germ-free mice, those same mice actually became obese, when other mice who were fed the same diet without those bacteria didn't show that effect. So people are just beginning to explore the implications that the microbiota of inside humans have for human health. And this sort of bacterial sequencing and non-human sequencing is going to be extremely interesting. In general, I propose that laboratory methodologies based on DNA or RNA can really take over diagnostics. When sequencing DNA becomes so cheap, what that means is that previously unthinkable things can be done. For example, you might use DNA or RNA in trained aptamers to pull down small molecules or to serve essentially as pseudo-antibodies and then just sequence those, rather than using a custom antibody or fluorescent assay, because the underlying technology is so cheap. Hopefully with this, I've convinced you that there really is a there, that we really do have the possibility of taking over medicine with genomic technology. So now let's say that we're going to take that 4 genomes per second as our goal and work through what we need to do in order to get there. Of course, the first problem we have to solve is how we're going to acquire all that. Data. Junior Mafia told us to get money. I propose that what we really need to do is get data. What do we have to do in order to sequence 4 genomes per second? One of the big problems here is that in computer science, really, a lot of the time that we work with genomic data, what we're really getting is just text data that's already come out of the sequencer, sometimes already after some pre-processing. So we're used to thinking of it as a string of characters, maybe just as a couple of bits, and then working on algorithms from there. Unfortunately, genomic data doesn't come for free. The world is inherently analog, and we need to be able to get that data into our computer somehow. In fact, genomic data is rarely clean. So this is raw data that comes out of one of the assays that we run at Counsyl called a Fragile X assay. There are some parts of the genome that currently are not accessible via next-generation sequencing technologies for technical reasons. Fragile X is one of those, and so you get data that looks like this, where essentially you're looking at fluorescent amplitude on the y-axis, and on the x-axis is a fragment length of a piece of DNA that you're trying to amplify, and what you're really trying to find out is how long that piece of DNA really is. This is a relatively clean trace, but a lot of them don't look quite so nice. Even when you look at next-generation sequencing technology, the data can be pretty hard to interpret. So one of the most popular platforms for sequencing today is Illumina, which is based on fluorescent terminating nucleotides during DNA extension. But even though you might get data, you might get bases out the other end of Illumina software, this is the raw data that you're ultimately working with. Digital camera images, really digital video of a microscope slide with millions and millions of these tiny glowing clusters. The way the sequencer works underneath is you have each of these islands represents one piece of DNA that's being copied many times over. They'll then flow one nucleotide at a time over the system and take an image. And so I believe this image was taken during a T cycle. And so you can see that any of these clusters that glow probably incorporated a T at that point in their sequence. However, they might also just be bright from another cycle and be noise. So really, you need to do a lot of signal processing in order to get good data out of this. Really, the problem is that because the underlying world is analog, there's a lot of work that has to be done before we even get to the sequence point in order to get data that we can use for machine learning, that we can use for genetic analysis. So let me give you a couple of examples. I've already talked a little bit about the Illumina platform. Another emerging sequencing platform is one from a company known as Torrent, recently acquired by Life Technologies. The way this platform works is also by copying DNA. It turns out that when you add an extra base onto the end of a growing DNA strand, you kick off a couple of side products. One of those is a proton, which changes the pH of the solution that it's in, as long as the solution is very small. So Torrent's solution is to have a set of very small wells carved into a silicon chip, so you have very small reaction volume, so that a few protons can measurably change the voltage in the system. Unlike Illumina, though, they don't use nucleotides that stop after just one extension. So if you have a run, for example, say of multiple T's in a row, the DNA strand will actually incorporate multiple T's, and you'll see a difference in the voltage. The big problem is that, first of all, there's a huge baseline on this voltage anyway, and as you incorporate more T's, your signal difference doesn't grow linearly. So the black trace here is showing just a baseline when there's been no incorporation in a well, and then each of the traces above progressively shows a voltage change as you incorporate a longer and longer what's called a homopolymer run. So you can see there's an interesting signal processing problem here. If we actually want to be able to sequence stretches of the genome, which may have very long homopolymer repeats, we need to be able to do really good signal processing in order to tease this data out from the underlying noise. Another example is the plot that I showed you on the left, Fragile X. So the etiology of this disease is such that you can't test it using current next-generation sequencing technologies. What we're looking for is a repeat of 3 bases, CGG, that might be repeated hundreds of times. That's a problem that's very difficult to handle, both because of the underlying chemistry, but also because short-read sequencing will have a hard time aligning a read that's all CGG. You don't know if it came at the beginning of the repeat, in the middle, or somewhere at the end. And accurately sizing this is really what we're trying to get at. Because when that repeat gets to be too long, that causes Fragile X syndrome, which is the most common inherited form of mental retardation. So currently in our lab, we have to run Fragile X using a completely different technology to how we run other genetic tests. And we do this by capillary electrophoresis. Now, this is a technique that was developed a number of years ago, but before we came along, the state of the art in calling Fragile X was actually just to look at these traces by hand and say, oh, I think I see a bump over there. That's probably going to be the call. The problem is that as the repeat grows longer, your efficiency of replication goes down nearly exponentially. So the alleles that you're most interested in, which may have hundreds or even thousands of repeats, are also the hardest ones to detect. That's a real problem when you're trying to do this testing at scale, because people will inevitably get tired, people will inevitably make mistakes. You'd like to be able to algorithmize this. So that's something that we did. We actually developed the first automated calling algorithm for Fragile X, which was an interesting research project in and of itself. The impact of that is that now, instead of a lab director having to spend 30 minutes per sample or per batch of Fragile X, now they might only have to spend 10 minutes reviewing a whole batch or perhaps a whole day's worth of batches. You've dramatically reduced the cost of labor, as well as dramatically increasing the accuracy and the efficiency of diagnosing this disease. So this is sort of an example of the concrete impact that research in signal processing, computer science, and machine learning can have on genetics outside the traditional realms of what's been looked at in bioinformatics. But let's get an idea of what needs to happen when we're acquiring this data. So I mentioned earlier that we're going to be getting like 3 gigabytes per second. But you protest 3 gigabytes per second over the entire world really isn't that much, right? The problem is that the raw data is a whole lot larger than the genome. So if we look at some data sets, I mentioned that the full genome, if you look at just the DNA, is about 750 megs. Really though, when you're doing short read sequencing, you need to read many, many copies of the genome in order to be confident in what you've called. Because otherwise you might think that what you've called as a mutation might actually be just an error in the sequencing. Furthermore, you need this kind of coverage in order just to do genome assembly and do the mapping onto the regions you want. So if you want 30x coverage, which is commonly accepted as a good baseline for doing SNP calling, you're already looking at 22.5 gigs. So we've increased our data rate to now 900 gigs per second. Even this, though, is after you've done base calling. When you look at the raw data, so for example, the Illumina images that I showed you a few slides ago, now for a genome just at 10x depth, not even 30x, you're already looking at 500 gigs and about 20 hours in the fast mode of an Illumina HiSeq 2500. New sequencing platforms are faster, but this gives you an even bigger problem. So for example, the Ion Torrent Proton P1, the system that I showed you a couple of slides ago, only takes 4 hours to run for 3x depth, but generates 540 gigs of data because you have to do such high sampling rates in order to get the signal processing to work. If you take 540 gigs and divide it by 4 hours, that gives you a data rate of 300 megabits per second. Now, that doesn't sound like very much when we're used to 480 megabit per second USB 2 or 10 gigabit Ethernet. But remember that this isn't something where we're talking to another digital system on the other end of the line. This is something where we're actually sampling data from the natural world. In terms of I/O peripherals that actually deal with real data, 300 megabits per second is a lot. The only thing really that we have right now that compares is high definition video or perhaps some radio systems. But even then, usually the radio systems are looking at data that's already digital. So you'll remember that when I showed you the slide from the NHGRI, that sequencing was scaling a lot faster than Moore's law. Now, people have made a lot of noise in doubly in computer science that Moore's law is slowing down, that we're soon going to reach the end of silicon scaling, that we're already at 22 nanometer feature sizes, and once we get a few generations down, we're going to hit the size of silicon atoms. Let's leave that aside completely. Even if silicon did continue to scale with Moore's law, if sequencing is scaling faster, then we simply cannot expect silicon scaling to solve the problems that we have in this area, right? There's just no way. What that means is that there's a real opportunity for computer scientists to do what engineers and device physicists can't. We have to be able to use algorithms to do what silicon scaling cannot. So there are a few concrete examples of how this has already happened in the genomics community. When you looked at read alignment, originally this was done using large-scale alignment algorithms like Smith-Waterman. But then new sorts of algorithms were developed that had better complexity for the short read alignment that comes out of next-generation sequencing. So the first generation of these short read alignments was using hashing-based methods, such as the tool named MAC. More recent tools are using tools like suffix arrays, suffix trees, and the Burroughs-Wheeler transform as embodied in tools such as BWA and SOAP3. Furthermore, we're going to need to use the transistors that we can have more efficiently. For a long time, even sequencing technology has been able to get away with either dealing with clock speed scaling or just getting more cores or just putting more nodes out there. But chances are, if we aren't going to get more transistors, we need to do something more interesting with them. So for example, people in genomics are already starting to leverage GPUs in order to make an impact. SOAP3 and Barracuda are both short read aligners that make use of NVIDIA GPUs in order to dramatically accelerate read alignment. But there's a lot of work that can still be done here. As I mentioned, the current state of the art in short read alignment uses the Burroughs-Wheeler transform, but that's something that currently is extremely expensive to implement on a GPU and just can't be efficiently done with the current architectures. So there's definitely scope for designing architectures that can handle these sorts of string-based algorithms rather than numeric vector algorithms in an efficient fashion. Furthermore, FPGAs are really starting to hit the fore. So a couple of years ago, Intel announced a deal where they would actually fabricate some of their processors with an onboard FPGA fabric in order to sell to certain embedded or system-on-a-chip markets. If you look at the specs for Ion Torrent's new machines, in addition to the sequencer, they also bundle in a server, which has, of course, 12 cores and it has 1 or 2 GPUs. But interestingly, it also has a couple of FPGAs. They haven't publicly disclosed exactly what they're doing there, but it raises the interesting opportunity that maybe really the way to do it is, instead of just going with conventional architectures, to write your own architecture and write your own hardware to solve these problems more efficiently. Finally, we need to represent this redundant information much more efficiently. Like I said, the genome at its heart is really 750 megs at a time, right? And if you're doing it at 30x depth, you're getting 22.5 gigs. But in some sense, you're really only getting 750 megs of data. Similarly, when you're getting 540 gigs out of an Ion Torrent instrument, really, you're only getting 3x depth, so just a few gigs of data. There's been some work in DNA-specific compression. So HapZipper was compression specifically for the single nucleotide polymorphisms and small modifications detected in the HapMap project. GSqueeze and DSRC are more recent, and they're specifically focused on the question of how can you represent short reads coming out of instruments in a more efficient fashion, so you're not constantly blowing your storage capacity. If we can work with this sort of compression, maybe design that into our algorithms, that can go a long way towards solving the data rate problems that we have. So some interesting problems, I think, really on the lower level part of computer science, when you're looking at numerics and signal processing, and then even when you're moving up into architecture and systems level considerations to handle this explosion of data. So let's say now that we have all this data, what do we do with it? Back in 1985, Schoolly D came out with an album with a classic track, PSK, what does it mean? Well, at that time, it stood for the Parkside Killers. But I think right now, we have a much more interesting question, DNA, what does it mean? Now that we have 9 billion genomes, postulating that the systems people have solved all the problems in the last few slides, what do we do with them if we're members of, for example, the AI community? What I'm going to argue is that genomics is really going to be the next big fruitful area in machine learning. So if you look at the mid-90s, a lot of the big things that came out of there were characterized by the explosion of the web. In particular, the explosion of cheap text data that you could easily get from the internet. So for example, a lot of algorithms on sparse graphs. PageRank is the most famous, but a lot of more recent algorithms coming out that do learning on sparse graphs and social or recommendation networks. Furthermore, we now have really effective machine translation. Barring the blogs that we'll take one piece of text, translate it English to Chinese, and then back again, and then try to find a fixed point. In a lot of cases, Google Translate really does work fairly well. There were recent tech demos, for example, from Microsoft, where they showed off real-time voice translation that even incorporated the person's voice. This is the kind of thing that can really only come about when you have mountains and mountains of data. A lot of you are probably familiar with the argument between Peter Norvig and Noam Chomsky versus formal methods in logic and statistical methods in logic. If you're not familiar with it, I encourage you to look at Peter Norvig's blog, but I think he makes the argument pretty clearly that really statistical methods have won, and it's the presence of huge corpuses of data that have enabled this sort of innovation. Finally, effective question answering systems. I think the best summary of this is people, if you saw Jeopardy, Watson did pretty well in that, right? So the abilities of search engines are always getting better, and even if right now you need one supercomputer just to answer Jeopardy, sooner or later that's going to be built in. And that's something that really you need to get a huge amount of data in order to mine. Argue that the big revolution in AI that came out in the last decade, in the mid-2000s, was cheap image data. So moving from text into the picture space. So digital images and digital video. What did that mean? That enabled the first really useful applications of a number of techniques that had been discovered before. For example, arithmetic coding is one of the most efficient methods for source coding that's known in information theory, and it would only reach real application in the H.264 standards for video compression. Part of that was because it's extremely expensive to implement in software as well as hardware, but part of it was because video is really an area where it makes a huge amount of difference to get that data rate down as low as you can. Similarly, Markov random fields have had a lot of success in computer vision, and high dynamic range imaging and in general computational photography are the kinds of things you can only get when you have huge amounts of image data. Similarly, effective computer vision, a great example of this is, very simply Google Street View, but more generally, the autonomous car projects and all the sorts of different computer vision projects that have been coming out that are really enabled by the fact that you can stick a cheap camera on anything and millions of people are carrying cameras around in their smartphones and uploading the data everywhere, which enables you to do really interesting things. What I argue is that as a consequence of the cost curves that I showed you earlier in the talk, the mid-10s are going to be characterized by an abundance of cheap molecular data that's going to come out of genomics. What does that mean? Well, I can't say for sure. It's easy to say all these things because we answered them in hindsight. I think it's very clear there are very interesting things that we can do in medicine with this, but there is one roadblock. The roadblock is not Destiny's Child, but I think the title of the song does say something. Say my name. The biggest problem that we're going to have in order to do this kind of research is conflicts with data security. So in the Affordable Care Act, as well as the HITECH Act that was passed earlier, there are strong incentives for medical providers in the United States to transition to electronic medical records. That's obviously going to be extremely powerful. When you have a large corpus of medical data in electronic format that you can pair along with a lot of genomic data, you're going to be able to do a lot of really interesting things. The problem is that those might actually be too powerful. Data de-anonymization is not just something that's fiction. It's a reality. As far back as 1997, a researcher was able to use hospital discharge data, which is required by state boards of health to be public, in order to de-anonymize who had particular conditions and combine that with public data in order to trace them back. That same researcher, along with a collaborator, was able to combine the discharge data along with genetic testing and actually de-anonymize the results of patients' genetic tests. In 2007, many of you are probably familiar with this work. Narayana and Shmanikov were able to de-anonymize the results from the Netflix prize data set and actually map users back to their particular preferences. And this isn't just an idle possibility. There's actually going to be a talk in a couple of weeks at the Personal Genomics, the Personalized Medicine Conference by Univeristy titled Genome Hacking, where he shows that it's actually possible to take whole genome data and de-anonymize that even when it's been stripped of identifying information. So that's going to be a really big problem because now the question becomes, how are we going to get access to this data in order to do any sort of machine learning on it? I think this is a really interesting area. Just one second. I think this is going to be a really interesting area in data security. At the same time, it may end up being a non-issue if this data becomes so pervasive that it's just easily accessible. Yes?
Anytime you use the word de-anonymize, you have to say what you mean by it. So for the Netflix data, what they did was they linked a record in the Netflix database with a record in a different database. And that wasn't the same thing as finding out the address and social security number of the person and so on. And it only worked for a very small number of records in the Netflix database. So what do you mean by de-anonymize in this case?
So you're right. The Netflix files was certainly limited de-anonymization data. I think the Sweeney papers might actually be more interesting because they were able to link these things to hospital discharge data and in fact also to voting records in order to get some identification. In some ways, it actually doesn't matter what I mean by this because the problem is going to be the specter of de-anonymization. The problem we have to deal with isn't the technical aspects of de-anonymization or what exactly it means. It's really the public perception of this data, whether it can be made anonymous enough that people won't fear for their medical records to be released and then for somebody to find their genomic information and tie all those together. The problem here really is a matter of perception in terms of getting consent for this research to be carried out. So, this is something that's, the analysis of data is obviously going to be a fruitful area in machine learning. But I think also for cryptography and security, there are some really interesting problems with data insecurity and provenance to be solved. But now once we have all this data and maybe we've made great medical predictions with it, what do we do with it? So Forgot About Dre is a great song off the 2001 album. But now that we have all this genomic data, we have to make sure that we also don't forget about the doctor. How are we going to help others use this fountain of data? One of the biggest things that we've learned in our experience at Counsyl is that there's a lot more to running a genetic test than just having a lab. Obviously, you have to actually get the sample and run the DNA test and get results and write the software and do the risk calculations. But getting buy-in from both patients and doctors is a really big problem. There are several very common objections that we hear out in the field. A doctor might say, I don't know what all these diseases are. How do you expect me to test for them? Or, I don't believe that all these things are important. Many of these are probably really rare. Who cares? Or I won't be able to counsel my patients on the results because I don't really understand what all of this means. Now, there are obviously genetics-based responses to all of these questions. For example, many of the diseases might be individually rare, but when you scale them over a large population, they're actually collectively common and cost a lot. Or I don't know what all these diseases are, well, I can just give you a genetics textbook. But really, there's an underlying problem here, right? It's novel information overload. Most doctors aren't trained in genetics. Almost no patients will be trained in genetics. And there's no reason that we should expect that they ought to be, right? There are a lot of other things that both doctors and patients have to deal with. Furthermore, genetics is one of the most quickly evolving fields of medicine. It's not just information overload, it's novel information overload, because the volume of new data is such that no one person can actually keep up with this. And we certainly can't expect every doctor out there to keep up with it. So let's take, for example, how reporting of genetic tests is currently done. Genetics is complicated, as I mentioned, and the current reports really aren't helping the situation. So here's an example of a report from another genetic testing company. Basically what it is an HTML table with some shadows where you list the data, you list the result, and here's an interpretation. And it really doesn't give you a summary, it doesn't help you understand what any of this really means. Furthermore, a giant list of diseases just on the front page is not going to scale. Right now, in the single gene area, it worked because you could say, all right, you have a check mark, you have an X, and that's your result. When you try to scale that over to 100 diseases, then you get giant tables that look like this. That doesn't help. What's going to happen in 10 years when we know a whole lot more about the genome? This approach simply isn't going to continue to work. Another example is analysis. So this isn't a problem that's limited just to doctors and patients. It's also a problem for specialists in the field, right? Or people who might be between amateurs and professionals. Anybody who's worked in bioinformatics is probably familiar with the UCSC genome browser. It looks something like this. I don't think anybody would call this a great usable UI, right? In many ways, nothing against UCSC. It's an amazing tool. It's very powerful and it gives you a huge amount of information. But in many ways, this is sort of the command line or the command line browser to the genome, right? There's a lot of power there, but it takes a lot of work to understand what's going on and in order to make it work. So what we need to do is do something better. So to take reporting for an example, what we've done in our tests is do something that we're calling design for understanding. So instead of just taking a giant list of results and dumping it on the doctor to interpret to the patient, what we try to do is lift that burden on both sides. So this is the front page of a report, and don't worry, this is fake data. You're not seeing anybody's information. But there's a summary at the very top. And even though we've tested for 100 things, we found that this fictional couple was only a double carrier for one thing, cystic fibrosis, and it brings that up right front. It says, look, you're at an elevated risk for cystic fibrosis, you have a 1 in 4 chance, here are a few options. If there was nothing detected, you would see that. But again, this is something which sort of alleviates a problem in the current scenario, but isn't necessarily going to help long term. So this is a tool that's useful for patients because they can see this very quickly and it has some understanding. It's also very useful for clinicians because it means that they don't necessarily have to find out about every disease. They can educate themselves on an as-needed basis when they see what comes up on a patient's report. So where do we go from here? Argue that one of the most interesting problems in HCI coming up in the next decade is trying to design the user interface for the medical genome. So, as an example, online education for computer science and for math and more generally science and technology students is really hot right now. There are a huge number of startups, Khan Academy, Udacity, Coursera, that are trying to tackle this area. But there's a really interesting parallel problem, which is how do we handle genetics? And we need to do this in a way that isn't just like putting students in a classroom, because ultimately, people aren't going to want to take a 6-week course on genetics just to understand what came out of their patient report. One angle that you can take this is consumer-focused education and exploration of genomic data. Now, there's certainly prior art for some of this. The My46 project at the University of Washington is a project where they're not only focusing on the interface, but they're also trying to focus on the privacy implications of genomic data. And 23andMe, with their consumer approach, has really done a lot to try to explain data to consumers and try to design some user interfaces around it. It's still a fairly niche thing, though, and so we need to figure out where we can take this. There's also a very interesting niche in provider-focused education. Remember that most doctors are not going to be genetic specialists, so they won't be expected to understand everything that comes out of a test report. What we need are tools that can summarize both the known information as well as current literature, so that doctors can stay abreast of these tools. It's not something where we can just expect them to subscribe to the RSS feed of Nature Genetics, Genetics in Medicine, Human Mutations, Science, Science Translational Medicine, and so on. We actually need something that brings the information that is relevant to them and relevant to their patients to the fore. This information needs to be integrated into the report. So as we learn more, many of the things are not going to be relevant to any particular patient. So you can't expect somebody to stay on top of everything. Probably the way that this is going to have to move is in a sort of on-demand sort of fashion, where when somebody finds out a genetic test result that's interesting, that they don't understand, they can easily bring up the information, and it brings it up in a way that's comprehensible to the particular user. I think that non-traditional interfaces have real promise here. So this is something that's definitely going to be an evolution in the medical community. There are still a lot of clinics there that refuse to use electronic ordering and ask that test results actually be faxed back to them. So for example, the nice PDF report isn't terribly useful. It's still a static paper-based entity. I think that as you have more penetration of mobile and touch technology, these sort of touch and dynamic interfaces have real promise for doing this kind of education. So let's recap. When we're talking about getting data, algorithms have to take the place of silicon scaling, because right now Illumina is moving faster than Intel. The rates of data coming out of sequencers are growing faster than our ability to process them. As a consequence, we might need to use non-traditional architectures, whether that means massively parallel hardware like GPUs, or designing completely custom architectures on FPGAs or ASICs. When we look at analysis, genomic data and EMR data really are the next frontier in large-scale machine learning. That's not to say that other areas are tapped out, but this is really fresh ground and somewhere where we can make a huge amount of impact. Similarly, in data security, this is going to be a really interesting problem to try to figure out how we can secure data in such a way that there's actually a buy-in from patients such that they will consent to have this data released in order that we can do research on it. And of course, we can't forget about doctors. Right now, neither doctors nor patients are fully prepared to consume genomic information. Right now, it takes a significant amount of buy-in just to get simple genetic information past that learning curve. And we really need to do more to improve that. I believe that doing some advanced user interface work is going to be critical for anyone to make sense of all this data. Questions? Yes?
You mentioned CPU and FPGA.
Mm-hmm.
So, what do you think about MapReduce-based algorithms can help the genomics?
So MapReduce Right, so MapReduce algorithms are certainly interesting, right? But if you're talking about MapReduce just running on a conventional cluster, then you're sort of running into the same problem, right? Where at best you're going to have linear scaling as you increase the number of nodes, right? My argument is that because the number of transistors you're getting isn't growing as fast as the amount of data that you're getting, that you need to do something fundamentally different in algorithms. You need to achieve super linear scaling with respect to the number of transistors. And so as a consequence, you might need to use a different kind of architecture to do that. That said, MapReduce-based algorithms are certainly very important because, even the CPU is not going away, right? And so you need to make use of as many cores as you can in order to bring more computational power to the fore, and that's proven to be a very powerful method for parallelizing methods. Yes?
What are you thinking about how the knowledge that backs up the data evolves and your responsibility to inform patients in the future?
Right, so I think it's a really interesting problem in genetics and bioethics, and it's one that nobody's resolved right now. The big problem is that it's not obvious. So on one side, it certainly seems like if you find disease information, or you find new information that suggests that somebody might have a disease in the future, that it's your obligation to inform them. Unfortunately, there's a competing side which says that if somebody was tested for one particular disease, they really may not want to know the results for the next thing. And that's actually one of the things that the My46 project is looking at. They collected data and they're trying to see, as more information comes out, do people want to know about this? I think this is something that right now nobody's come to a consensus about, and the way it's working is if a clinic asks for an updated report, it'll be issued. But ultimately, it's a question of medical autonomy, right? Whether the patient actually wants to know this information or whether they don't. Yes? Yeah, so proteomics is another very interesting area that I didn't discuss very much. So in some ways, the information that you get from proteomics is similar to that which you might get from RNA-seq or transcriptomics. Obviously, you're getting it one step further down the pipeline after translation. I think that's really interesting. I didn't talk about it today because I think the routes to getting data out of proteomics are not evolving as fast as those from DNA technologies, right? Right now, the best ways you have to get that kind of data are things like protein mass spec or protein microarrays, occasionally SPR, and those just aren't scaling as fast. So I think in order for proteomics to make that a similar sort of impact to what I think genomics will, we meaning biochemists and biophysicists, need to find a way that you can change that scaling curve to really accelerate how much information you can get.
So in your Moore's law slide, it looked like the bottom fell out, but the last 2 or 3 data points look like it might come back to that slope, and that remains to be seen whether it actually keeps falling or whether it goes
Right. Yeah. So that's totally right. So there's sort of a linear trend, then a very sharp line, then sort of another one. And so I think the question there is really going to be how fast can technologies continue to evolve, right? So I think with silicon scaling in general, the route has been fairly clear. You use lithography at smaller wavelengths. You have to add a few things like maybe immersion-based lithography, and you have to change the device physics. But fundamentally, the objective that you're trying to achieve is very similar. The sequencing is a little bit different in that the fundamental technologies underneath sequencing have actually been changing every few years. So about a decade ago was when pyrosequencing and 454 chemistry first hit the market. Then you had Illumina's terminator-based chemistry. Now you have ion torrents, sort of voltage-based sensing methods. In the future, Oxford Nanopore is promising systems based on nanopores. There are indications of things that might be able to do with microscopy. So I think there's still a lot of ground that's being gained there. Whether it's converged, I think at that point, then you start to ask questions of whether Moore's law is going to continue at the same pace. If that slows down as well, then maybe sequencing slowing down still maintains the point.